here, you can see that how autoencoder working. It is like super amazing here, because the thing is here, the input data was 2-dimensional, and I map it to 1-dimensional. It's like using one number, you can learn this distribution. Is it possible? One number, one exact. So it's like we're kind of using one dimension, like any line you can draw, and then I can kind of find all these layers. But the point is, because that line is like a non-linear, I can do that. But actually, if I switch to another distribution, like I don't know, let's say 2 moon, then you can see that, okay, should I do that? See, then it kind of finding all this thing to be like an anomaly as well. So you can't just use one dimension to be able to capture all the information here. So the compression was too much here. So that's why the number of layer, the number of dimension that you're using for your embedded space is super important. If you use something super small, you will lose all some information. If it's super big, it won't make that much a difference. Maybe if you might be able to easily maybe reconstruct it, anything. So that's why you better play with it and have the right number. Mm-hmm. It's like big enough number.
Mm-hmm. So I think what you are saying is impossible or improbable that you have, there is a nonlinearity between the full representation and the latent. But the transformations between latent space and the initial full distributions, the sample space, the original space, it is non-linear. Or we can even consider linear. So when it is linear, then if you do PCA or you do the best low dimensional fit in L2 norm, which is the same, you try to take as much information as possible in your latent space with you, and the situation when you have a huge effect in latent space, but it translates into a negligible effect into full representation. It is impossible.
No, so, but the thing here is we're labeling outliers.
Yes. Who was saying that? You were saying that, right?
Necessarily, the reconstruction error necessarily has to do with while you labeled the outliers. Does it make sense?
Trying to process it.
So getting back to the session, we're all done. Sorry, we'll continue after. Want to go to the VAE?
I just had one quick question about the exercise.
Okay.
Even with different parameters, when I achieved lower loss with the original loss function, like at the end, it didn't always translate into better outlier detection in terms of the F1 area under the curve.
Which can make sense actually, right? Because like we're dealing with a deep neural network, which you want to learn the distribution, and because as our friend was trying to say, what is convex, which is not convex here, you might end up with any different local minima, and that's why the loss, it means how are you fitting the training data, but you haven't seen any outlier. So being better for a day was not in any part of your cost function at all, right?
Here the outliers are mixed in again, right? And then the credit card data set.
Is it?
Well, for like last time, I think.
you train?
I'm using normal, see? So it's not part of
Okay.
it.
Okay.
So the model hasn't seen any of layer based on the pure data, and it's trying to learn it. But if it will learn learn it in a way that those off layer, which happen to be the layer that I care about,
Which is labeled scaled.
which will be the third one, those number will get worse a score based on the current autoencoder or not? The answer can be yes or no. The thing is, because right now I have a list of outlier that I do care about, but tomorrow I might have new list. The day after I might have new list. So the model might work for the other one, because outlier is not part of the data, it's just a bunch of noise, right? So you are right. Having overfitted model for your training data doesn't necessarily mean you will be better for finding outlier.
So if all we know, if the goal is, okay, here is some data, you're gonna train it. There's, in this case, I don't think there was like a validation set or something.
I would say
So how do we know
I would say the reverse of it is true. It means if you can't fit your data, you won't be able to use it at all.
Yeah.
If you can fit it, then you might be able to use it for anomaly detection. So the first thing, you should be able to fit your data, and then from that moment, you're hoping that you should be able to catch all the things which are not similar to my normal data.
Okay.
So, did we get any good number that we can? Has anyone?
How do we, when we declare the model, when we compile it, how do we stop it from printing the model?
From doing what?
From printing it out. Maybe
You can change the function. You don't want to see the model?
Well, I mean, I know what's in there, right? Like, it's just showing me the stuff, and then there's going to be like a whole bunch of this stuff before I see the results.
Okay, if you go up, because I wrote the function in a way that kind of
It will definitely do.
give you all the information that you need. But if you go down
Yes.
here, if you go down a bit,
Summary.
yes, if you remove that, you won't have the information.
Yes.
So, I'm assuming that we are all on the same page almost. To train a model, I just want to see you all training a model. Training a model. I want to make sure that you all are all the hands are dirty here.
Study.
Okay. Good. So you can make it the 10 to be 5, 20 to see which one will give you actually better result. Is 10 good enough? Can we compress it even more than that to make it to be 5? Is 20 is the best? That's what I'm trying to make you to kind of understand about the data. So that's how you can actually learn your data to see is like you can see the autoencoder as a way of feature extraction. You are just extracting those features which is important. And if you can actually construct the data just by using 5 features, then maybe you don't need all those 31. You can just compress it to 5 and just use it from that moment.
Is there a rule of thumb, like first thing, it's related to your original, like how many features in your original data? That is like a square thing or something?
No, that's the problem. No, because it depends on the distribution of the data. If let's say the one Gaussian data that they have,
Yeah.
I could kind of map it with one dimension. I can have, I don't know, lots of more sample or something like that. So it's not about the number of dimension you have, it's about
How complicated it is.
Yes, exactly. So I couldn't see any good number so far, but I'm assuming that you are getting good number. Maybe I shouldn't have shown you the code, so. Okay, let me move on then. I might move on. Wait. Should I move on? Should I wait? Any question? I just want to make sure that everything is clear. So, any question? Raise the question.
So this histogram with training digits and anomaly digits.
Can you see that?
How do we use this histogram? So if you scroll up to the previous example.
So this histogram is just to show you how the model is performing if you know the label. Usually you don't know the label.
If I know.
Yes.
So this is the training set or the test set, but it is like given set. With label set.
Yes, I use the label set to generate the chart to tell you that if the model is actually working or not.
So for a working model, we expect some separation, good separation between blue and
not a separation, I would
it?
say. Usually the thing that will happen would be like that. See the MNIST, which maybe the model was too small for MNIST, you couldn't capture it. And you can see the overlap is huge. At the very end, yes, most of them are outlier, but usually there was a huge overlap as well. And just imagine when you're dealing with the real data, there is no label. So that will be the whole distribution. So you can cut it wherever you want. And then based on the cut, you might have more outlier or even more false positive as well. But to show you that if it's actually working or not, I'm kind of, because I have a label, I can cheat here. I can say, okay, see how autoencoder is working. Then you will here, because I want to make sure that you are understanding the idea and make you believe in that idea. So tomorrow, when you don't have any label, you can have a distribution and you can be confident that maybe if you just use the mean distance or something like that, the thing that you're getting maybe will be actually outlier.
So on this histogram we see that it is not working, or it is not working well, because we can't.
But still, you can see any distance after 0.1 is almost outlier.
Okay, so we can catch some anomalies,
yes,
but
not all of them. Exactly.
But if we had, for example, first blue landscape, then a gap, and then orange landscape, that would be the ideal situation.
Yes, exactly. Maybe you are saying something like that here, that if you believe that there is no orange here, maybe we have something like that. If you see it as a normal, maybe it's like that, or not. But the thing is, like, it depends on your data. But that's the dream, that if you can actually separate them just by using autoencoder. So that's how you can actually play with it and find a bunch of outlier in your credit card data. I'm just going to say it again. Even if you have sequential data, you can just use exactly the same technique. That's the beauty of deep learning and neural network techniques. It doesn't depend on anything. You can have any kind of type of data. Then you can, for the encoder part, you can have convolutional neural network, you can have LSTM, you can have hierarchical neural network, you can have, I don't know, a bunch of layers with attention or anything you want. And then you can try to reproduce it again. So you can get as complex as you want to be able to deal with any kind of model that you want. And one more thing, here we are using autoencoder, which means we are trying to reproduce everything. In practice, sometimes we don't want to do that. Like if you have, I don't know, super complex data, like let's say insurance claim data, financial transaction data, or something like that, sometimes you can be more smart about it and say, see, I don't want to just produce the input as output, because not everything in the input is important. Like, I don't know, so in the input, because the problem with the autoencoder is it will have same weight for every single thing in your input data. It won't care which one is more important. So let's say maybe one of them is actually the cost of the claim. One of them is maybe something about that transaction. You're just saying that that one is more important for me than the other one. So you can come up with the weighted one as well, or you can ignore the not important one, just predict. That's what I say is kind of like a self-supervised learning. You can just maybe predict the cost one, or I don't know, some more, like you can just select the more important one and just ask the model to do that. Or you can go even one step further, have a function of the input. Let's say in transaction, in all those things that you have in a financial system or in insurance claim that people are claiming. Instead of even predicting the whole claim again, or even a part of it, we can claim what will be the cost, the average cost in the next year. So then it has nothing to do with the current claim, but you should be able to learn the pattern in your sequential data to be able to predict something like that. So then from that moment you're saying that if the distance is different, maybe is it if you know the information from the next claim or something like that, then you can use it as your new distance metric. So the same thing is like the autoencoder is the first choice, simplest one, but you can make it as complex as you want.
But then for say, then if like you want to predict churns, right? Like the survival thing, or like who's gonna die, right? Then will you like also, how do you also model or say the gap between events in that sequence?
That's something that you can come up with your own data. So then that's a different topic, that how can you add time to your sequential models, but there are different techniques that you can actually do that. So you can use the time difference, even if you're using LSTM for the forgetting gate, you can kind of apply the time, the difference between them to trigger the forgetting gate, something like that. So there are lots of technique for that, but the thing is, depends on your data. You can use any kind of trick you want, and the whole idea is, instead of coming up with any kind of new things, you can use your current data to do some supervised tasks like the thing you're doing here, to be able to tell difference between normal and not normal one. So next, VAE. Are we on?
Oh, we're being on
Okay.
this whole time.
Okay. And you have some result as well. Good, you have 41. Perfect. Nice. So, what's VAE? VAE, as we said, is exactly like the autoencoder. The only difference is, see, all these things here are exactly similar to autoencoder, but the only thing is we are coming up with the two sets of value here. We're calling the first one mean, the other one is like a variance, let's say, and then we are doing a sampling from it, and then we are trying to use the decoder to regenerate the data again. So that's VAE basically, in just few lines of code. So the only thing here is like for the cost, for the loss, here I'm making a my VAE loss, which will be reconstruction one, which will be the MSE. So here even you can use binary cross entropy, because I'm giving you the option that you can switch between them. And you're adding the KL divergence. And the only thing that it's doing is, as I said, try to make that probability that you're generating to be similar to a normal distribution, or if I just want to make it simplify it as I can, it will try to make sure the mean is close to 0 and the other one is close to 1. So from that moment, you will have some constraint about it, and even you can use the reconstruction loss or the difference between the new embedding to a normal one. So you can have two score. You can use both of them to say which one is. And say that, okay, that was the, so here the distribution is changed. Maybe I should actually increase it to 0.2. Maybe you have more thing over there. I'm missing them. Yeah, see, there were more. Let me actually increase it to 25.
I seem to have lost your hangout. Oh, no, never mind. It's my end. Don't worry.
You have low battery.
Yes, I have to do. For the exercise, I will do that. So as you can see here, that was how VAE is performing for MNIS. So even maybe it's still 0.1 happens to be a good number for me here. And then I have all those outliers over there, but still there is overlap. Exercise, you can say number 2, to run it for autoencoder. Again, I'm giving you some, not hint, actually the code, but I want you to do the same thing for VAE and make my result better. Exercise number 2. I should get my
No. Wait, but do you just look for an argument? Is it something that?
Nola?
Yep.
Internet was down just now. It lost about 2 minutes because you sort of just for online people repeat what you said for the past 2 minutes.
Okay. Sure. Are we on?
Yeah, we're on now.
So the thing that we said in the last couple of minutes was that's VAE.
Oh, it's not?
We said the only thing that we are doing here is super similar to autoencoder. The only thing that we have here, we're just mapping, we're kind of, instead of just having embedding layer, we have mean and variance, and we are sampling from it, and then from that moment is exactly like decoder of the autoencoder. And I define my own loss, which is reconstruction loss, plus the KL divergence loss, which the only thing that is doing is trying to enforce the embedding to be close to normal, which means I can then use both of these loss as a metrics for finding outlier. And then I run it for MNIST, and then I tested it, and then I said that see some of the image, like 7 was super similar to 5 because of the constraint of the Gaussian here. Everything will be mapped to something close to normal, and the decoder part will map it to something probably that we have seen before to maximize its own benefit. So that's why the beauty of here. The beauty here is like because one of the thing in variational autoencoder is actually you can interpolate between two samples that you have seen before. It means if you have one is here in your space, and you have seen 2. If you move from 1 to 2, the number will actually gradually change from 1 to 2 when you're reconstructing it. So even if you have any point in between, it won't be exactly like 7 that you have seen before. Maybe 7 happens to be somewhere that it was close to 5 actually. So that was the thing that we reduced. That was the result. And then we said that maybe that should be a good threshold for finding outlier in your MNIST data. But still we have lots of overlap because maybe the variational encoder was not good enough for MNIST. And then as an exercise, we are doing same thing again, but this time for variational autoencoder.